For most of human history, the Earth's magnetic field has been invisible, silent, and taken completely for granted. We do not see it, we do not feel it, and yet it is one of the most important forces keeping life on this planet possible. Without it, Earth would not look like the blue world we know today. It would look far more like Mars, cold, dry, and stripped of its atmosphere. The magnetic field acts as a planetary shield. It surrounds Earth in a vast protective bubble called the magnetosphere, deflecting dangerous charged particles coming from the sun and from deep space. Every second of every day, the sun fires a continuous stream of high-energy particles toward Earth called the solar wind. If those particles reach the surface unfiltered, they would damage DNA, disrupt ecosystems, and slowly erode the atmosphere itself. For billions of years, Earth's magnetic field has absorbed that punishment for us. But in recent decades, scientists have noticed something unsettling. Measurements from satellites, observatories, and geological records all show the same trend. The magnetic field is weakening, not collapsing, not disappearing tomorrow, but measurably weakening on a planetary scale. And that raises an important question. What exactly is happening to Earth's magnetic field? Why is it happening? And what does it mean for our future? To understand why scientists are concerned, we first need to understand what Earth's magnetic field actually is and where it comes from. The magnetic field is not produced by the crust, the oceans, or the atmosphere. It originates deep inside the planet, far beyond anything humans can reach. At the center of Earth lies a solid inner core made mostly of iron and nickel, surrounded by a molten outer core composed of the same metals but in liquid form. This liquid outer core is extremely hot, under immense pressure, and constantly in motion. As Earth rotates, the flowing molten metal generates electric currents. Those electric currents create a magnetic field. This process is known as the geodynamo, and it has been operating for at least 3.5 billion years. As long as the outer core continues to move and circulate, Earth maintains a magnetic field. The magnetic field extends tens of thousands of kilometers into space. On the side facing the sun, it compresses under the pressure of the solar wind. On the night side, it stretches out into a long magnetic tail. This structure deflects most charged particles away from Earth, funneling some toward the poles, where they create auroras. The northern and southern lights are not signs of danger. They are visible evidence that the magnetic field is doing its job. However, precise measurements show that the strength of this field is not constant. Since the early 19th century, Earth's magnetic field has weakened by roughly 9% on average. That may not sound dramatic, but on planetary timescales, it is significant. More importantly, the weakening is not uniform. Some regions are changing faster than others. The most concerning area is known as the South Atlantic Anomaly. This region stretches from South America to southern Africa and represents a large dent in Earth's magnetic shield. In this zone, the magnetic field is significantly weaker than the global average. Satellites passing through it experience higher radiation levels, which can cause computer glitches, data corruption, and instrument damage. Some satellites are even programmed to shut down sensitive systems while crossing this region. The South Atlantic Anomaly is growing, drifting westward, and splitting into multiple lobes. That behavior strongly suggests changes deep within Earth's outer core. Scientists believe that complex flows of molten iron beneath Africa are disrupting the magnetic field above. This does not mean the field is about to vanish, but it does indicate instability. Another reason scientists are paying close attention is because weakening magnetic fields have preceded magnetic pole reversals in the past. Earth's magnetic poles have flipped many times throughout its history. During a reversal, the north and south magnetic poles swap places. These events are recorded in ancient volcanic rocks, which preserve the direction of the magnetic field at the time they cooled. On average, pole reversals occur every 200,000 to 300,000 years, but the timing is irregular. The last full reversal happened about 780,000 years ago. From a geological perspective, that means Earth is overdue, although overdue does not mean imminent. A reversal could begin thousands of years from now, or it could already be slowly unfolding. During a reversal, the magnetic field does not suddenly flip overnight. Instead, it weakens, fragments into multiple poles, and becomes chaotic for thousands of years before stabilizing again in the opposite orientation. During this period, Earth's magnetic shielding would be reduced, allowing more solar and cosmic radiation to reach the atmosphere. This leads to a natural concern. If the magnetic field weakens further, what would actually happen on Earth? The first and most immediate effects would be felt in space, not on the ground. Satellites would be exposed to higher radiation levels. Electronics would degrade faster. GPS accuracy could decline. Communication systems could experience more frequent disruptions. Astronauts aboard the International Space Station already receive higher radiation doses than people on Earth's surface, and those doses increase when the station passes through weak field regions like the South Atlantic Anomaly. A significantly weaker magnetic field would complicate future human spaceflight, especially long-duration missions. On the ground, life would not suddenly be wiped out. Earth's atmosphere provides an additional layer of protection, absorbing much of the incoming radiation. However, increased radiation could raise cancer risks slightly over long timescales and affect biological processes in subtle ways. Some animal species that rely on Earth's magnetic field for navigation, such as birds, turtles, and whales, could experience disorientation. Another serious concern involves the sun. Solar storms, also known as coronal mass ejections, occasionally send massive bursts of charged particles toward Earth. When these storms collide with the magnetosphere, they can induce powerful electrical currents in the atmosphere and on the ground. In 1859, a solar storm known as the Carrington event caused telegraph systems to fail and auroras to appear near the equator. If a storm of similar magnitude occurred today during a period of weakened magnetic shielding, the consequences could be far more severe. Power grids could be damaged, satellites disabled, and global communications disrupted for extended periods. Modern civilization depends heavily on technologies that are vulnerable to space weather. So why is the magnetic field weakening now? The honest answer is that we do not fully know. The outer core is inaccessible, and its behavior can only be inferred through models and indirect measurements. What scientists do know is that the geodynamo is inherently chaotic. The flow patterns of molten metal change over time, driven by heat escaping from the core and interactions with the mantle above. Computer simulations suggest that periods of weakening are normal in Earth's magnetic history. They do not automatically mean a reversal is underway, but they often precede significant changes. The current weakening could represent a temporary fluctuation, or it could be an early stage of a long transition that will unfold over thousands of years. Importantly, Earth has survived many magnetic reversals before. Fossil records do not show evidence of mass extinctions directly caused by pole flips. Life adapts, the planet endures, but modern technological civilization has never experienced such an event. Our vulnerability is not biological, it is technological. This is why scientists are concerned but not alarmist. The magnetic field is weakening, yes, but it is not collapsing tomorrow. There is no credible evidence that Earth will lose its magnetic field entirely in the near future. Even during reversals, the field does not disappear completely. It becomes weaker and more complex, but it continues to exist. The real issue is preparedness. Understanding how the magnetic field is changing allows engineers to design more resilient satellites, power systems, and communication networks. It allows space agencies to better protect astronauts. It allows governments to plan for space weather risks that are often overlooked. In a broader sense, the weakening magnetic field is a reminder of something deeper. Earth is not a static machine, it is a dynamic, evolving planet with forces operating far beyond human control. The ground beneath our feet is moving, the core beneath that ground is flowing, and the invisible shield above our heads is alive, shifting slowly over time. We often think of space as hostile and Earth as safe, but safety is not guaranteed. It is maintained by natural systems that have been operating long before humans existed. The magnetic field is one of those systems. It does not care about technology, economies, or civilizations. It follows the laws of physics and the internal rhythms of the planet. If the magnetic field continues to weaken, humanity will adapt, just as life always has, but adaptation requires understanding. And understanding begins with paying attention to invisible things that quietly protect us every single day. The weakening of Earth's magnetic field is not a countdown to disaster, it is a signal. A signal that our planet is changing, as it always has, and that our future in space and on Earth depends on how well we respect and prepare for those changes. The question is not whether Earth's magnetic field will change. It already is. The real question is whether we are paying enough attention to live safely beneath it as it does. Like, comment, subscribe.